Hello, I'm Hein, and this week I will take some brief review of short channel effects. As we talked about a lot several times before, when we scaling down the device, there are some problems because the distance of the distance between the source and drains get close, so the electric field between the source and drain is more stronger than before we scaling down the device. So it is a little bit hard to control the channel by controlling the gate bias. So in this situation, there are some problems. The first thing is punch through. Punch through is the phenomenon which the depletion region between the source and drain get overlapped deep inside in the substrate. In this situation, it is hard to control this region by controlling the gate bias because it is too far. So in this region, that can make the leakage current. To improve these problems, we can use some knobs like making a heavily doped substrate or SOI structure, or making some using some strain relaxed buffer. These knobs can decrease the leakage current but it also have the problems like self-heating problems or uh, unwanted band gap, etc. So still we have to improve the knobs to solve these problems, the punch through problems. The second problem is breathe up. Breathe up is the phenomenon the threshold voltage become lowering because the density of the electrons, the carriers, get increased at the channel, so it is easy to turn on. But it means the easy to turn on the device is not good because it is hard to control the turn on bias on the device. The third problem is weight reductions. It occurs when the channel and the depletion shares the charge. So it's similar with the Briti-Loroff. The threshold voltage get decreased. And the first problem is Briti reductions. The third problem is Briti reduction. So to solve this Briti reduction problems, we can use some knobs like controlling the junction depths and controlling the thickness of the gate dielectric. It means we have to control the gate coupling to control the channel. The first problem is DBO, the drain-induced barrier lowering. When the device have short channel, when we apply the drain bias on it, the carriers in source is more easy to move the other side because the energy barrier is small, and when you apply the bias on the drain, the slope get more steep. It means it is easy to turn on the device at the small voltage, and it leads to the increase of the subthreshold swing. The fifth problem is velocity saturation and mobility degradation, but this problem I mentioned in the last video, so today I will skip this problem. As we studied at the physical electronics, the electric field of the device is the biggest in the boundary of the junction. So to decrease the electric field in lateral directions, we have to use the junction engineering. For example, the LDD, lightly doped drain. We add some area which is lightly doped at the boundary of the junctions. Uh, by using it, we can make a shallow depletion region at the junction, and it can lead to the decrease of the electric field there. The second method is using the pocket implant, which is called halo junctions. We can make a pocket at the junction to block the expansion of the depletion region of it. The pocket is made which is the same polarity of the substrate and the opposite polarity of the source drain. By using this method, we can improve the SC problems, but not enough. So we have to try the other knobs to improve it. From now, maybe we will talk about these problems this semesters. Thank you for listening to today's review and see you later.